Welcome to this webinar about smart energy systems and AI in the green transformation. I've been looking forward to this webinar today with some great speakers. It's part of DIKU Business Club's webinars, Computer Science Impact for Industry. And today's webinar is organized together with Energy Cluster Denmark. My name is Pall Skött, and I'm Head of Business and Innovation at the Department of Computer Science at the University of Copenhagen, DIKU. And the University of Copenhagen has a rather long history with energy research. This year is 200 years ago, Hans Christian Ørsted discovered electromagnetism as professor at the university. But when it comes to collaboration in the energy cluster, we have a rather new history, and only recently we joined the energy cluster. So today is a way to get to know the energy industry, the cluster, and present some of the opportunities related to our research and collaboration at DIKU. So today's program, we start with Jørgen Christensen, the CTO of Dansk Energi. We'll tell about how smart energy systems can ensure a cost-effective green development of the sector. Then a presentation from startup, CTO Emil Mahler from Utiligize, and about forecasting of electric vehicles. Then we have a short break, go get a cup of coffee, and after that, Stefan Sommer from DIKU about AI and machine learning in the power grid, and Glenn Napier from Energy Cluster Denmark will join us after the break and tell about the energy cluster, and we have an open discussion where Trine Krogh Bomsma from the Department of Mathematics will join us. She a researcher in operational research, and tell more about that just before the discussion. So, with no further ado, give the word to Jørgen, well, some short information before that. We will record this webinar and send it out, break it into smaller pieces and put it out to YouTube. And if you have Q&As and comments, please put it in the chat or in the Q&A. So we can take a few questions in the presentation, but most of the questions will be at the end. So I'll give the word to Jørgen about smart energy systems and the energy sector.
Yeah, okay, well, first of all, thanks a lot for the invitation and introduction. I'll make you could say, a short introduction to how we are going to develop the energy sector for the coming 10 years. And it could be some kind of a ride. I don't know whether tree canoeing here is scared or looking forward to an enjoyable ride. I know how I would feel if I was staying there, but anyway, I really look forward to the coming 10 years. And I'll take, you could say, two short introductions. One is really the economic part of it. Why should we go towards a smart energy system? And then with one single example, and I'm quite sure that Emil afterwards will tell much more in detail how you can use technology related to that example, because it's around electric vehicle. And then I'll take a bit more time on, you could say, some of the threats going towards smart energy system, the cyber issue we have around that. If we look towards what we're really working on, is we have this climate target, or this national target, the 70% reduction of carbon emissions in 2030. Well, the target is to reduce emissions by 17% compared to 1990 emissions. And just a few figures on that. We have reduced with 35%. So, well, anyway, we have used, let's say, 30 years to go half the way, and now we have 10 years to take the second half of it. And to be honest, I think we have, hopefully we have taken a lot of the easy solutions. So now we have all the difficult solutions. Of course, you can say during these last 30 years, computer technology, digitalization have evolved a lot, and I think that's really what we need to go, you could say, to take the last and very, very difficult step. one of the reasons that it's quite interesting in the electricity industry is that there is a quite clear forecast that electricity consumption need to double from this year, 2020, to 2030. So we really have to increase the consumption of electricity by a factor 2 in 10 years. And that's a huge challenge, because you cannot build an infrastructure, a traditional infrastructure, to handle this increase in consumption. And why should we increase consumption so much? Well, we have to substitute a lot of fossil fuel. And one of the obvious ways is to change from fossil fuel driven vehicles to electric vehicles. And one of the forecasts is that we need to have around 1 million and 1.5 million electric vehicles in 2030. And that's a huge challenge to incorporate them into the energy system. And we also need to change a lot of gas and oil heated houses to heat pumps. And these heat pumps can be on an individual level, and it could also be into, you could say, the district heating system. And if we have, and we need to succeed with that, and that really basically implies use of smart grid technology or smart technology. We have this climate partnership for energy, and that delivered their report in March this year. And then they had actually made, you could say, a full forecast how to fulfill this goal. And it's a huge report, and I'll be happy to send it to you afterwards, or link to it. But they have really seen what is, you could say, if you look into the traditional grid infrastructure, what kind of investments do you need towards 2030 to fulfill the requirements that you can supply the double of electricity consumption? Well, if you have, and if you start on the left side, if you have the traditional consumption, and just say, well, we have to, you could say, refurbish, develop the system towards 2030, but with no increase in consumption, that is actually a cost on around 56 billion Danish crowns. That's really the cost for running the existing infrastructure, just to you could say, service the existing consumption. Well, now we need to double the consumption, so we end on around 70 terawatt hours. If we, you could say, use smart energy technology, and I'll give you a single example on what that could be later. The need for investments in this infrastructure is about around 20 billion Danish kroner, or 23, which means that in this infrastructure sector, we need actually to invest, using smart energy technology, nearly 80 billion Danish crowns towards 2030. Well, that implies that we use smart energy technology. If we allow, you could say, the new consumption to use the grid as dumb devices, we actually have to increase the investments to 110 billion crowns. So I tend to say there is around 30 billion good arguments for using smart energy technology in this development. And to be honest, even if you had all the money, or even if you think, well, I like the old technology, I want to do it the old way, to be honest, we cannot build this infrastructure in 10 years. So we need to utilize smart energy technology all the way around. And I'll just give you one very brief example, and I really hope that Emil will go into details on that. I expect that. I haven't coordinated it with Emil, but I know him very well. And I apologize that some of the figures here is in Danish. But really, what we mean by doing it smart, this is a typical consumption curve for a household. The dark green here in the bottom is the typical consumption of a normal household, which means that you sleep during nighttime, getting up in the morning, start to utilize your electric devices, go to work, and then when you come home in the afternoon, then you start your cooking stove, and that's really the device in your house that uses most power. And we tend to cook at the same time in Denmark, everybody. So we have the evening peak here when everybody is cooking. And that really, it's really the peak that demands the capacity of the grid. If you put in and a heat pump into a household. Let's say this household have either a gas heating device or oil device. Then you put in a heat pump. It has a more, you could say, a constant energy consumption during the day. It can be more flexible. I'll not spend time on that. But if you take a typical electric vehicle, that what really happens is that you park it during the afternoon and then you just plug it into your charging point, and then it will typically charge at the evening peak, and which means that you have to increase the grid capacity. And that was really what I called the dumb scenario. That's where you needed the 110 billion Danish krone in investments. If you can do it smart, level it out during the nighttime, because we basically need our vehicle the next morning. We don't need it 9 o'clock in the evening. We need it 6 or 7 o'clock in the morning. That really reduces the need for capacity in the grid. And I hope Emil will tell a bit more about what you need to do to fulfill this. And it looks very easy on PowerPoint. I think the technology is available, but there is a huge challenge also to get the user involved and get their acceptance of letting out some of the control of their consumption. But that's doable. And that's really what, if I should say, that's the smart energy thing. And then I'll switch to, you could say, the challenge around that. And that's really the cyber threat against the energy system. Because if an electric vehicles, 1 million electric vehicles get controllable, then they can also be hacked. And the challenge is you get a really brief introduction how to an energy system runs. It has to be in real-time balance. That was the old system. When you plugged something in, then you just started the power plant to increase the production to fulfill the consumption. The new system is that we're going to have a lot of flexible devices, wind turbines and PV production, and we cannot control, you could say, the outcome of that in the same manner as a power plant. And the smart energy thing is really that now a lot of our devices, the electric vehicle, the heat pump, becomes controllable. And I think a lot of you will be familiar with the IoT term. So really, and that would be internet connected. And that's really a challenge for an infrastructure provider like us, because we used to have full control of this system. And now a lot of these devices are getting into the internet. And who are ensuring that, you could say, that these devices are compliant with the highest security standards? Because they're not a part of the infrastructure owner's control, they're part of the user's control. And when I am on cyber seminar, I tend to ask people, how many are ensured that their Wi-Fi connection point has the largest patch, has the largest firmware? And I think the record is 30% of the attendees. And what can happen if somebody gains control of all these small devices? Well, this is how you could say security of supply is in Denmark. We have the best system in Europe, or nearly the best system in the world. We have a very small interruption. Then you see we have 3 years where we have, you could say, large interruptions. And all of these interruptions here in the bottoms, that's around between 1 and 2,000 smaller interruptions in the lower voltage grid. You have something digging over a cable or something like that. These events is a single event. That's an event on the transmission system where you get you could say, a cascade effect in the system. So where this is a result of 2,000 events, this is the result of a single event. And actually, this one was due to some digital communication issues. And that's really what happens if you gain control of 1 million electric vehicles. That's where we can end. And the traditional system has no control on these devices on the cybersecurity level. And that's really the question. How do we build this system where there is about 30 million good reasons for doing it in a smart energy? How do we build it safe? Because it's not me as an infrastructure owner that should be ensured that can ensure that the electric vehicle is updated to the newest security standards. I cannot assure that this privately owned devices has the latest security patch. And that's really one of the big challenges, and I hope some of the attendees or some of the other panels have good answers on that, because Otherwise, we were not going to harvest this economic benefits on 30 billions, and we have to do that for the society. I think that was a very brief introduction to how smart energy systems and 30 billions.
Be a need to make some solid investment plans that bring down costs in spite of increasing costs because of the increasing demands due to electrification of transport and heating. And then the app is used to log a lot of data maintenance and also collect data. Collecting data is really key when you're trying to make the right decision. And our what's unique about our asset management platform is it builds upon future loading scenarios. So we take in inputs, political targets for electric vehicles, heat pumps, and solar, and see what impact that has on a grid. So, and from that, we can actually say something about the optimal placement and sizing of assets, like electric vehicle chargers. And then also another key part of this is lifetime estimates of these assets. These are really expensive things that can last 50, 60, 70 years. So it's really about making the right decision now, because we're going to be living with it for a long time. The green transition doesn't start in 10 years' time. It actually started 10 years ago. Everything we were putting in the ground has to last through the next the coming wave of electric vehicles. One of the things I thought I'd talk about today is our experience with electric vehicle charging. One of the things that our software does is it links to Denmark Statistik, the national statistics database. It also links to BBR, which has a lot of information about buildings. We link it to Bilstatistik, which has all the car importer data, so we can see how many electric vehicles are being sold every week. So it's collecting all of these data, but when we speak with countries around us, companies in Southern Europe, for example, they don't have this wealth of fantastic public data. Because we believe it's very difficult to have a software company that will only survive in Denmark, and we're looking abroad, we've started looking for more general ways to understand how EVs will impact the future. And one of those is looking at orthophoto data, which is overhead imagery. It's very high resolution. It's available in all countries. And we can run machine learning on it to identify where cars are parked, where they're in motion, and then also understand what that means when half of them or all of them are electric, and how it will load our infrastructure. What we get is some really interesting heat maps. We've got heat maps like this for EVs, solar, and heat pump. And then we can see in which areas there are going to be problems, which areas we need to upgrade the infrastructure, and in which areas we need to activate flexibility. So that means shift consumption or production in time. So it's out of the peak hours, as Jørgen was saying, into the nighttime, for example. So here at the highest density, typically in, of course, most populated areas, you can get up to 1,000 electric vehicles in 2030 per square kilometer. And I think that, so where I live on Amager, there's an underground car park with 500 cars underneath. And it could typically be somewhere like that where half are electric. One of the really interesting things that comes out when you combine all this amazing data is you start to see some interesting correlations between EV ownership and income. That's what we've got on the left here. We also have EV ownership, house size, and on the right here we have EV ownership, income adjusted, and then which parties people vote for. So on the left here, if I should just try and explain that, on the x-axis we've got disposable income. And the most affluent area in Denmark is Klampenborg on the east coast of Sjælland. There, so far, around 4% of cars are electric. down in one of the poorest parts of the country, Odense Nordøst, it's almost zero. So there's quite a strong correlation between income and EV ownership. And that also means that there's quite a strong correlation between where the first electric vehicle chargers are needed. There's all sorts of moral implications of this, which we haven't thought about so much, but it's definitely an interesting area. And then when we adjust for income, we can see it's typically the left of center parties that explains EV ownership more. So there, if you, once we adjust for income, if you vote for Alternative or Enhedslisten, we can see that you're almost 40% more likely than the average voter to own an electric vehicle today in 2020. On the other hand, if you vote for Venstre, then you are 35% less likely to own an electric vehicle today than the average voter. Of course, there are a lot more voters of Venstre, and it's very easy to get into some discussions with them about how they don't really like these results, but this is what the data seems to show us. Okay, so I'm hoping, it's always a little bit dangerous to do a live demo, but let's see. Have I still got you with me?
Yes.
Yeah. So this is a distribution feeder in Silkeborg. Silkeborg, actually I was born just around here. The red lines are 10 kilovolt lines, the blue lines are 0.4 kilovolt lines. So it's low and medium voltage. We've got some high voltage coming in and supplying the area. You've got the yellow boxes, which are cabinets, and they're connected to houses and apartment complexes. I'm just going to turn on the overhead imagery so we can start to see. It takes a few seconds to load the car identification. But what we can begin to, yeah, there we go. So now we can start to see where are cars now. We've also been working on, are they on a road? Are they in transit? Or are they just parked? There's some parked cars here. And now, what does this mean for the, if I just turn off the imagery again, what does it mean for loading of these cables? Because it's, the loading, it's a voltage drop, it could be a voltage increase. It gets a little bit complicated here, but what is the utilization of the infrastructure given these electric vehicles and solar and heat pumps? And here we have the lighter colors are at 100%. This is a flexibility scenario that I'm showing, and the darker colors are at 0%. So we can see here, this cable here, it's going to be fully loaded in 2035. And then we only have two options. We can either activate flexibility or we can go and dig up the road and put a new cable down. And there needs to be a cost-benefit analysis. Basically, you need to do it at a large scale. We also have these transformer points, which are the central distribution points that the cables connect to. And there we also see that some investment is needed. But generally, it's what we're seeing is the low and medium voltage will require significant investment and activation of flexibility to incorporate these electric vehicles in a socioeconomic optimal way. I can just take another example. Something else we've been looking at quite a lot is some of the fringe cases, including fast charging at petrol stations, which somebody pointed out to me the other day. I shouldn't be calling them gas stations. They should just be called charging stations in the future. So this is quite interesting. I'll just put on the autophoto again. So this is actually a petrol station in Jutland, and there are two transformers supplying this area. And we've modeled this area with 8 350 kilowatt chargers, the really fast ones that you just need a few minutes to charge your car in the future. 8 in each direction, north and south. And there we can see that there is no way getting around upgrading these transformers. You're going to have to upgrade them. The cables are okay though. So the cables, they have enough capacity, but the transformers don't. So it's really a dynamic system that we need to optimize. Something else we've seen is looking at batteries. Can batteries be used instead of these transformers here? Because isn't that the future? Well, actually, our models suggest that they won't be. The batteries are not a cost-effective alternative for this kind of case. Although batteries do make sense to invest in, but typically to trade on the energy markets in the future. One of the inputs to this model is future energy prices from the Danish energy outlook. They do a forecast once a year, and there you can see over the next 15, 20 years, there's going to be huge opportunities as we integrate wind, as we integrate solar, big changes in price that mean storage is required. It's really just a signal for storage. Okay, so that was my little demo. I think it went okay. And then I'll just round up what comes out of this. Well, you get, sorry for the Danish here, but you get an investment profile. And what we could see, especially probably in the 2030s, that there's going to be quite a lot of additional investment. From a percentage perspective, there's a lot more investment required in town areas than sort of city areas rather than more rural areas. But most of Denmark is rural, and most of the costs will continue to lie there. But percentage-wise, these things are shifting towards the town. Okay, I hope I came on just in time there.
You are exactly on time. It's quite impressive with the presentations. Well, a question for you, Emil. How difficult or easy is it for a small company like you to get into this business that with the large energy companies and so forth?
I mean, it's that's an interesting question. It's you can say in a way it's beneficial in Denmark because there are so many small utilities, and you just need a few visionaries to take the chance on something new. Most won't take the chance, and because it's a risk taking a small company, working with a small company. It's also not what they're historically good at. They're good at digging holes, and they're not. They don't think in terms of data-driven concepts. On the other hand, what we have seen in Europe is that most European utilities have big innovation centers and innovation funds, so they're constantly kicking off proof of concepts, and we don't have the same concept here in Denmark because the utilities are too small. So it's I think it's as good an area as any to get into, also because it's so interesting, and that's half the battle. It means that it's non-stop, but they're certainly challenging from. It's a totally weird area because these are natural monopolies. They have no competitors. What is driving their change isn't what drives change in most of the rest of the world. So it's you need to learn a few tricks.
And the opportunities for you to get into the European market, how's that?
It's okay. We get some offers to do proof of concepts. I think it's easier to reach out to Norway and Sweden, where it's more similar to Denmark. You have a couple of really large European utilities. NL is one of them. It's a bit hit or miss. We've not succeeded with the really big ones yet, but I'm patient. We just need to keep on developing, and at some point it will happen, I think.
Yes, and collaborate with both the Danish sector and the universities. That could maybe also get an angle to that.
Yeah, so we've written some research applications. Well, I should say from that perspective, we keep on being invited from my. I did my PhD out at DTU, We get some great invitations to join some of these research projects. It's important that we only do the ones that are completely relevant for us, so we don't get sidetracked. And from that perspective, yeah, there's lots of soft money, and it's because I think I get the call because there aren't that many people taking a chance and trying to do what we're doing. But
ideas, and then of course this needs to be connected to the actual sort of technical world where the power grid is actually running. So sort of making, I see my role as getting the nice ideas and pushing machine learning to be able to work here, but then I'm also very interested in actually making it work in the energy sector, and this is something that I would like, of course, your input on and so on. Okay, so the STAR project is a project funded by the Forskel or EUDP Foundation. It's a collaboration with DTU. DTU is heading it, and the overall aim is to ensure stable operation of the energy grid when we transition from having centralized, small number of centralized power generating units like coal-fired power plants to large numbers of decentralized fluctuating energy production units like windmills and solar and so on. Actually, what Jørgen also talked about early on. So we can measure the state of the grid by installing what's called PMUs or phase measurement units in the grid, and then we like it, of course, to be the grid to remain stable to prevent blackouts. And there's different kinds of stability here. There's long-term stability in the sense of if the wind doesn't blow, there's no energy in the system, so we cannot charge our EVs, for example. But there's also short-term stability, which is that we need to produce the right amount of power sort of at the moment, and we also need the system to be in a nice stable equilibrium state. And this is called voltage stability and anchor stability. And this is what is targeted in the project here. So what we like to do is to get this information from the grid on a very large scale, then acquire it and feed it into a computing system that produces some indicator of the overall system state, and also gives information to the operators on preventive measures, or actually would suggest maybe preventive measures by themselves. So to be more specific, if we look at the power grid with these PMUs, then they are, as it is now, fit into a SCADA system, and the system that we are or have been building then takes the data from the SCADA system in real time and stores it or provides a snapshot of the grid state and feeds these data into first a high performance platform that does a lot of computations to assess the state of the system, and then afterwards visualize it to provide input to the operator, and also suggest these preventive measures and so on. And the DIKU part is here in the high performance platform because we need to, in real time, assess the state of the entire power grid, and for example, the entire Danish power grid. And this is a pretty large system with many nodes, so there's some numerical algorithmic work to be done in order to make sure that this can be done in real time. So the visualization would be something like what you see in this sketch, that if the grid is in a stable state, we are in the green area, and then if the state becomes stressed somehow, that sort of is beginning instabilities in the grid, then we move towards the green state, and if we get to the red state, then we are in risk of a blackout. And so this would sort of be a summary of the entire grid state connected to sort of produce this picture, and all this algorithmic work would be in order to place our operating point on such a picture. And then of course we would like, if we are in the green, in the yellow area, to output suggestions for how to control the grid so that we move back into the green area again. And in the project, then we test the algorithms that we develop both on real-time simulators, but also at the power lab DK facilities at DTU, where we can run it on actual power systems like the Bornholm power system that you see here on the image. Okay, so let's focus a bit more on this, the algorithms, the numerical algorithms, the DIKU part of the project. So we have a large power grid, and we would like to get the stability assessment out of the current grid state. This is often done by first computing the Thevenin impedance of the network. So it's sort of, in short, in a few words, it's the impedance seen from each of the power generating nodes. And this can be, this Thevenin impedance can be computed by removing all other nodes from the network in sort of a sequential manner, or it can be seen as a linear algebra operation where you do an LU factorization of the system admittance matrix. So the admittance matrix comes as a matrix where each row and column corresponds to a node in the grid, and then you do sort of linear algebra on this system. Well, this has to be done in real time, and if we're looking at large grids, so for example, in the visualization you see here, it's an 8,000 node grid, then the factorization can be a bottleneck, or it will actually always often be a bottleneck. And the major problem is that when you remove nodes from the system, then your initially sparse system becomes denser. And if you do linear algebra, then dense systems, in sort of factorizing dense systems is a computationally difficult task. So what we have developed in the project is a new methodology for handling this case, where we call it reduced factor solve, where the reduction is a removal of nodes in a way that does not lead to decreased sparsity, and then afterwards there's a sort of partial factorization of the system. And what you can see in the lower right graph is that even for very large systems, the rightmost one is this 8,000 bus system, we can compute the Thevenin impedances in around 3 milliseconds. So that is sort of what enables the real-time output of the Thevenin impedances, and then from that also the security assessment or the stability assessment. So we package all of this into it's C++ code. It's of course has to be very efficient for this real-time operation, but we package it also in Python modules so that it can also DTU researchers and students can interface with the code and use it in an easy, accessible way. And just to give you sort of a hint, that these relatively few lines of Python code that you see in the lower right is enough for setting up a small power system and then do the factorization and the Thevenin impedance computation using this very optimized backend code. Currently, we are taking this idea even further to enable, again, real-time computation on even larger power systems, and this is by having a sort of a geographical or regional division in the grid. So one can imagine if one goes to very large systems like the entire European grid, that it's not necessary to look at the interaction between each and every node in the grid. But you could perhaps look more regionally, compute interactions there, and then sort of sum them up afterwards on a more on a global level. And this is sort of the way to approach that is to not look just at the admittance matrix, but give it that a hierarchical decomposition. So now we have sort of a cost to find view where the courses view is for example, the entire European grid, then comes countries, then comes the regions within each country. And then at the lowest level, we have the individual grid nodes. Now we can do a factorization again, where we make a tree with the interactions between these different levels in the tree, and then we pass up and down the tree and get a nice factorization out of that. And if the grid has certain properties, which is sort of mainly that the rank interaction between the different parts of the grid is low, then we get a reduction in the complexity of the the factorization algorithm, basically. So enables us again to do very efficient computation of, for example, Thevenin impedances on extremely large grids. So that is what we have done so far in sort of the numerical algorithms side. And now I will go to two examples of projects that we are setting up now, and that we will hopefully get funded and look at in the coming years. So the first one is to use machine learning and AI to analyze the streams of sensor data from the power grid. And the idea here would be to do it on a very large scale, so we acquire as much sensor data as possible on a very fine time resolution, and then we will apply sort of modern neural network technology for sequential data, for example, recurrent neural networks, or maybe even more modern like transformer networks and attention modules and so on. And the idea would then be that we could predict the state of the different nodes in the grid. Maybe we don't have full observability of, for example, a transformer in the grid, but then we could correlate the measurements we have with what we know sort of would be the state. And then we could run forward in time and predict future state of the grid, or failure risk, or do health assessment, or you maybe predict what would be a good control action for the operators of the grid. So if we could do that, or hopefully when we can do it, then what could be the impact? Then, yeah, well, it could, for example, be state estimation of let's say, transformers from chip measurements. So let's say that you're interested in how stressed a transformer is, and you cannot measure it realistically sort of from direct measurements, because it's either too difficult or it's too expensive to install appropriate sensors. Then we could measure something which is more realistic, like temperature and like energy flowing through the transformer and so on, and then correlate this with the actual state. So that is one case. Then we will be able to predict localized stress in various scenarios. If the system have learned the dynamics of the grid, then one can sort of extrapolate if you input various scenarios. You could do, as Emil also talked about, intelligently schedule maintenance or upgrade of grid nodes, or you could predict future load scenarios by running sort of forward in time the simulation. The challenges, which is also, as I said, I'm doing basic research here, so I like the difficult parts, but that would be to apply these modern sequential data and neural network designs to power grids. Many of these techniques are used for, are designed for text processing, automated translation, and so on. And of course, there's some work in actually making that work on power grids with the graph structure. Then we'll need it to be robust, which is of course very important. If we have a lot of measurements coming in, we cannot ensure that they come in at the same time and that we don't have outages and so on. And then we like it to be robust between grid topologies, so we can transfer the learned model, but also if we have, let's say, a line break, then it shouldn't, then the trained network should be able to sort of cope with that. And then there's also the sort of practical side in acquiring and storing very large time series data sets from the grid. But I think, as I see it, the potential thing would be we should measure and store as much data as we can. So if you make the parallel with language or text processing, then right now text models are trained on data sets that comprise the entire internet. So all text on the internet are processed through these models, and then suddenly sort of new use cases appear, because you can do things that you couldn't before when you go to these very or extremely large data sets. And if we could do something like the same for energy systems, then new possibilities might open up. And then by the end, I'll make one more case for possible use of AI in the power grid, and this is inspired by the the case of the SAP project, where we did this modeling of the grid state and the stress to do the security assessment. We had the numerical algorithms, and then in the end, there would be a human control using the visualization to run the grid. But now we could also imagine just learning this. So this would be using reinforcement learning to learn what would be appropriate control actions. And then the idea would be that we could potentially scale up to very complex grid with very stochastic production and load dynamics that we couldn't handle with analytical models. Maybe that would be infeasible, but we could do it having the AI sort of learn the dynamics. Yeah, so for that we would need very fast simulators, because reinforcement learning algorithms needs millions of examples to train properly. But there's some current work that is pointing to that is feasible, for example, to train neural networks to simulate the grid. And this could be incorporated with the reinforcement learning algorithm in model-based reinforcement learning, for example. And then again, we have this graph structure, and we want to be invariant to topological changes in the grid, and we want to be able to train move the trained model between different power grids. So transfer learning with the graph structure. Yes, that was what I have from my side. So just to sum up, you saw an example of numerical algorithms applied to the power grid in the SAP project, and then I sketched these two projects that we are working on setting up, both on time series analysis of data acquired from as many points in the grid as possible, and then by the end reinforcement learning to control the grid. Thanks for the attention.
Yes, thank you very much, Stefan. And to all of you, remember to write your questions down in the chat and the Q&A. And also, that's kind of like when you're talking about the but maybe you should stop share your screen so we can see the.
Yes.